Hello, dear students. In this session, you will learn how to play with your NMR data using the software MestReNova. So I'll tell you a few details about how to use the software and how to manage your spectral data to get maximum information from it. So let's begin. And let's start our MestReNova. So this is the MestReNova interface, and you can see a lot of different options here. We will try to learn each of them and their use in this session. For starting your NMR analysis, the first thing you need to do is to go to File and click on New Document, right? And you can see this window will open, which is empty. We have to insert our NMR files or NMR data files into this, and then we can play with it. Let me tell you about some of the options that we can use, and later on we will apply that to our spectra. So here is the new document, and if you click open, you can go to any of your saved data folders and you can import the data files from there, and you can use the directory as well. You can save your spectra that you have worked with. You can save it in different options. You can change the page setup from here. You can even print your spectra from here. You can export it as PDF. You can find some recent documents here and some recent files, and from here you can exit. The next tab is the edit menu, and you can see here a lot of options: undo, redo, cut, copy, special, paste. You can insert some objects, and you can even paste some properties like NMR graphics and NMR integral speeds, etc. You can delete something. You can annotate like curved arrows and select line, arrows, rectangle, ellipse, etc. You can format the text that you have typed, and you can also change the alignment with this button here. You can create a new page. You can edit page titles, and you can add some preferences from here. Here is the view button, the view menu, and you can see that we have layout templates here. You can select the one that you need, and you can customize the menu bar, the toolbars, etc. These are the pages, right? So here you can see, let me close this. These are the pages right here. You can see it's written here. So if you click on this, and these will disappear, right? So if you don't want to see those pages here, you can click on that button and it will disappear. If you click on it again, and they will appear. This will show you all the pages that you have in this document. It's just like the thumbnails on the left of a PowerPoint presentation. So it's up to you, whichever format you think is appropriate for you. From here you can change the view. You can use the toolbars here, which one you want to see on top here, and these are the different panels you can see here. Like, you want to close everything, you can see the line fittings, the data analysis, integral manager, multiplet manager, phase correction, etc. All of these options are present here. We will discuss each of them in detail, and from here you can change the intensities. You can also find these options here on top, and these are the cuts. These are the blind regions. You can edit the blind regions as well, and that's the staked mode that you can find here on the left hand side, and that is the 2D plotting method that you can also find here on the left hand side. And these are the different traces that you can use. This is also found here on the left hand side. These are the different databases in which you can search the formula. You can search the peaks, the multipliers, the MS search, numeric search, etc. You can do all these searches. You can process your data from here, like for example here you have the f1, f2, the frequency 1, frequency 2, and you can see the FID as well, the processed FID, original FID, and spectrum after Fourier transform. You can do the phase correction, you can do the baseline correction, you can symmetrize your spectrum, and you can do a lot more things here. Here's the analysis. These are the references, and I'll tell you what this means when we start. These are the peak pickings, like if you want to label any peak, integrations are here, the multiplet analysis, assignments are here, verification, and some other things. And here you have the line fittings, how you want to see your lines, the data analysis here. That is the stake option, the mass analysis, from which you can get the elemental composition, the peak detection, molecule match, the spectrum prediction, etc. From here also you can do some predictions and so on, right? And you can select how you want to view your document. So some of these menu bars have been added here as toolbars, and we will learn how to use them when we have the spectrum. So to have a spectrum, you can import any file from here, from this open option. When you click it, this window opens and it will lead you to that site from where you want to import your data files. So we have some NMR data that are my own compounds, and all of these folders contain the data files for different NMR techniques which have been carried out for this compound. The code is here. So we have the proton NMR, the carbon 13 broadband spectrum, the depth 135 is here, and we also have the 2D techniques. So let's start with the proton NMR. You double click it. Here we have the FID, and you click on FID, select it, and then click open. Here we are. So that is your proton NMR spectrum for this compound. The label is here, the code is here, and here you see the technique name is written down here. So you can tell from here which spectrum is this. Now you can see that we have a very intense peak here, and all the other peaks are very small. This peak might belong to the solvent. This analysis, this proton NMR spectrum was recorded in methanol on a 600 megahertz spectrophotometer, and you can see that here we have the NMR scale, the frequency scale in ppm, and here is the intensity. And at 0 ppm you see a very small peak which belongs to the TMS, of course. So now we have to bring this spectra into a readable, understandable format, because these peaks are very small. We cannot interpret it, or we cannot see it clearly. So the first thing you need to do is to enhance its intensity, right? So from where you can do that. So we have all these options here, and like you can save it, you can print it, and that is the undo and the redo button. And here you see the zoom in button. So you have the range from -3 to 16. If you don't want to see the regions which are empty, so you can just zoom in from here, click on zoom in, and you can select the region from 0 to 8, because this is the region where you can see all the peaks. The rest is empty. So how you can do that is, first you click on zoom in, and then you double click on one end of the spectrum and then drag it like this. So you drag it to the end, the other end, up to which you want to see your spectrum, and then leave it. So now you can see that your spectrum, or the whole screen, shows the spectrum from 0 ppm to about 7.5 or 8 ppm. If you still want to go back to the original position, so you can zoom out, and when you click on zoom out and you click in the center of this page, you see it's zoomed out. So you don't want that, you go back and zoom in. You can actually drag it from left as well, like this. Here. Now again, the peaks are very small, so you just want to increase the intensity. See here, you can see the full spectrum, and here you can pan it. You can bring this baseline up here or down there by using this pane option. Let me click it, and you can see it goes up and down, right, when you drag it. So we don't want that. It's perfectly set here. Now here is that option, right? So if you click on this, that will increase the intensity of the peaks. You click it once, see it increases. You click it again, and so see the peak intensity increases. If you think it's too much, you can decrease it, yeah, like this, and you can bring it to a level with which you are comfortable, right? And this is the crosshair. So if you click it, it will give you a crosshair on your cursor, and you can correlate different peaks, right? But we don't need it right now. And that is the cut option. So if you don't want a part of your spectrum, so you can click on this. And for example, I don't want to see this TMS signal, so you just double click here and then drag it, and see it's gone. But that will show a cut here on the baseline, so anyone who wants to see your data will know that you have cut something from here. So the baseline is cut here, and I'll do the undo with Control-C, and it comes back, right? So this is the cut option, and here we have, you can edit the blind regions as well from here. Down here we have another set of different options. So we have F1, F2, that is set processing dimension to F1, that is frequency 1, this is frequency 2. F1 is for this proton NMR spectrum. F2 and F1 both are active. You can see F2 is inactive because it's a one-dimensional NMR spectrum, so you don't have the second frequency, the second dimension. If you have a 2D NMR spectrum, then both F1 and F2 will be active. Here we have a drop-down menu, so you can see 4 different options: the original FID, the processed FID, spectrum after first Fourier transform, and spectrum after second Fourier transform. So 3 of them are active. The 4th one is inactive again because it's not a 2-dimensional spectrum, and I will show you later on when I insert the 2-dimensional spectrum here, then you will see that this will be active, right? So if you want to see the original FID of this molecule, just click on it, and here is the FID for the proton NMR spectrum of this molecule, right? If you want to see a processed FID, so you click on this and see it changes, and that is the processed FID. If you want to see the frequency domain spectrum, this is the time domain spectrum that we have discussed. If you want to see its frequency domain spectrum, and that can be obtained after Fourier transform. So the spectrum after first Fourier transform looks like this, right? Again, you can zoom it in, and that will give you the region which you want to see. Okay, then here we have the apodization. So apodization is also like cutting the FID. We will not go into detail of what apodization means, but that is to cut the tail of the FID. You can do that with the help of this, and you can see a small scissor here at the tail of the FID. That suggests that you can cut the tail of FID using this option, right? This is the Fourier transform option, the drop down, and you can see that you can do different types of corrections, apodization, truncation, zero filling, and Fourier transform with this, right? Then we have this option of phase correction, right? So what does this mean? If you think that your spectrum is out of phase, you just click on this drop down menu, and you can do automatic correction, but if you want to do manual correction, you can just click on it. And here you have some guideline. Click here and drag mouse up or down holding the left button for pH 0 correction, or right button for pH 1 correction. Hold control key for fine tune. So what you do is you just uh, click on your left mouse button, hold it, and then you move your mouse up and down, and see the phase of the peaks, it changes, right? And so the peaks are actually going out of phase into phase. If you think your peaks are out of phase, you can do the phase correction from here, but our peaks were well and truly in phase, so we don't need this option. But this is a very good option if your peaks are out of phase in any way, right? And then we have here the baseline correction. If you think your baseline is not straight, so you can also correct your baseline, right? So if you click on this baseline correction and then click OK, it will correct your baseline, right? It will straighten it. And then we have the reference. So this is the reference for your peaks, and I have told you earlier that the solvent signal can be used as an internal reference. So from here you can actually correct the chemical shift values of your peaks. If you think that your peaks are not in the correct regions or correct positions, so what you do is you click on this reference, and you see that you can select a peak right here. So this is the solvent peak. You click on this, and here we have the chemical shift value of this peak, that is 4.877. If you're not sure whether this is the correct position for this peak, which belongs to methanol, you just go to the solvents option here, and you will see all the different types of solvents that you can use in NMR. So all the deuterated solvents are here, and you know that you have carried out your analysis in methanol, so go down and find methanol somewhere, and here it is, right? Methanol T4. It has two peaks at 4.870 and 3.310. So the peak that we have selected is this one. So you just click on it and then click OK, and you see that your peaks will move to the correct position. And now the new position of this peak is 4.870. Previously it was 4.877, right? So now your peaks are in the correct position. Okay, the next option here is peak picking. So you want to know what is the exact chemical shift value of all the peaks. So you can do it automatically, but if you don't want to do it automatically, because an automatic option will select all the peaks, there might be peaks which you don't want to select. So you can do a peak by peak selection manually, right? So this, I think, is a better option, to do it manually peak by peak, and then you can select any of the peak, and its chemical shift value will appear here. But before that, I just want to increase the intensity of these peaks a little, just to be sure. And because we have some multiplets, I want to see them clearly. So if you want to see the exact multiplicity of these peaks, because it's not clear here, you just zoom it in, right? Just select that region, and now you can see them clearly. So you can see that this looks like a quadrat, and that quadrat is split into two. Each arm of the quadrat is split into two. That looks like a quadrat, a doublet of a quadrat, and this looks like a multiplet. So if you want to select these peaks peak by peak, click here, And now you can see that each peak will be selected. So you click on this, you see its chemical shift value appears here. And click on this one, this, and this. So you see all the peaks are marked here. And you can also select these peaks right here. If you want to see the whole spectrum, go back like this, and then you can select the peaks which you want to label. So you select this region and then go back to peak picking, go to peak by peaks, and then you can select any of these peaks here. This is also a multiplet because we cannot clearly tell what is the multiplicity of this signal. And similarly, you can select any of these peaks and then go to this option. Okay, I just by mistake clicked here. So you see that all the peaks are marked automatically. If you don't want that, just do the Control C option, click on the drop down button and go to peak by peak, and you can do it peak by peak manually. All right. If you think your spectrum is pretty much clear, there are no impurity peaks which you want to ignore, you can do the automatic picking as well, right? So that's up to you how you want to proceed. And so this is how we do it. This is the methanol peak, 3 at 3.3. We just leave it just to be sure that we don't confuse it with the peaks from your compound. And then you zoom it again and select this region. So again, go here and you do the peak by peak picking. So we are working here in the aromatic region. 7 to 7.5 is aromatic region. These are the peaks in the regions from 5 to 5.5. These might be olefinic signals, and you can select them manually. If you want to do the automatic pick, you can do that as well, right? So we have picked the peaks. So you know the chemical shift values. The first thing you need is the chemical shift value. The second thing you need is to know how many protons are there in one signal. So that can be, this information can be obtained from the integration value. So this is the tab for integration. You go to the drop down button, and this is the auto detect, but you can do it manually from here. And now this is an important part of this. If you can identify a signal that you think is for one proton, like for example, I assume that this peak here is for one proton. So I go to the manual setting, and now you see this option here with the cursor, and you have to select the region. So for integration, you have to select and start from one end of the peak to the other end. So this peak starts from here and it ends here. So I'm going to select the region starting from here and ending here. And you see that the integration here is 1. If you want to change it, just double click here and you see that it's normalized to 1. That is done by the software. If you don't like this one, you want to normalize it to say 0.5 or 0.9, or you can normalize it to 2, but I think that this is a signal for 1 proton, so I normalize it at 1. If it is at 1 already, then you can leave it, and this peak will be taken as a reference now by the software. So if this region counts to integral 1, which is this here, you can see the integral curves. Let's see how many protons does this peak represent with reference to this one. So if this is 1 proton, let's see how many protons are here. See, it's 1. If you cannot see this, I can just increase the font. So if you don't like the font size, you can just right click on here and you'll see a lot of options, right? So you can do the peak search, the multiplet search, the zoom in, the full spectrum, phase correction, baseline correction, peak picking, integration, reference from here as well. You can do the cut, copy, paste as well. You can delete or paste anything here, right? But go down to properties and here you will have some options. So this is the general button and all of these parameters can be set according to your desire, whatever font size and font style you want to keep. The second option is the grid. Now you see that behind your peaks you can see this grid, the vertical and the horizontal lines. If you don't like it, you can deselect the horizontal and the vertical grid, and when you click apply, you see the grid is gone. But I usually keep it checked, so I check it again. You see the grid will be back, right? And here we have the color for the grid. So you see it's light gray in color. The line width is 2.5, so you can change it if you like. This is the 1D NMR peak, and you can see that the style is a line spectrum. You can use the crosses, you can do the circles, but we usually keep it in line. And you see the color is maroon. You can see the maroon color here for the peaks. If you don't like the maroon color, you can actually change it to any color. Let me change it to this pink color and click apply. See, the color has changed to magenta, right? And let me change it to say blue, apply, and it is blue now, right? But let me keep it to maroon. Where is maroon? Here. So I go back to maroon, click apply, and here it is again, right? Then come here to scale, so you can also select the line width and the margins, etc. The horizontal margins, the vertical parameters are here, right? And here are the peaks options. So in the peak you can see that we have the font size, the font color, everything is here. Then the line width, the units, the decimals, etc. are can be set. So if you click on this font, you will see the font style here, the font, the size. So if you cannot see the chemical shift values here, just increase the font size, right? And then click OK and apply. See, the font size increases, right? If you want to increase the decimal, like this is in 2 decimal figures, and then if you want to keep it, up to 3 and click apply, see, it's in 3 significant figures. If you want 4, you can increase it to 4, click apply, and now it shows 4 decimal points, right? Okay, then we have the integrals. So integrals are also in a very small font size, so you can click on this and you can select the font from here. You see the size is 8. If I want to keep it at 14, click OK and then click apply. See, it has increased. So now you can clearly see that it's 1. Here are the multiplets. So in the multiplets, again, you can change the font color or the font style or the size and the decimals, etc. Everything. Here are the integrals. Integrals can also be changed from here. And then we have the fittings, the assignments, the predictions, etc. Right? So I click OK and close this. Now you see that if this was normalized to 1, this is 1.03, which is almost 1. So this is also 1 proton. And then we select this area. It is 0.98, which also shows 1 proton. If I select this region from here, this 0.96, that also shows 1 proton. This is about 1.03. That also shows 1 proton. And then let me select these peaks. So go back to integral, manual, and I select these 2 peaks. So let's see how many protons it represents. 2.14. It means both of them represent 2 protons, so 1 signal for each of the protons. These 2 peaks show 2 protons, so 1 for this, 1 from this. This should be 1, and yes, it is 1. This should be 1. Okay, this is 2, and this also shows 2 protons. This peak bunch also shows 2 protons. This bunch shows 2 protons. This should also show 2 protons, yes. And this one should also show 2 protons. Yes, this is the methanol. You don't need to integrate it. So when I click on the full spectrum, you see that every peak is marked now with its integrals. So you sum up the integrals, you will get the total number of protons, right? Okay, then we have the J values, right? So you can actually calculate the J values from the chemical shift values. You know how to calculate the coupling constant now. So for example, we have this peak. You just enlarge it, you zoom it in, and it looks like a double doublet, which is not marked actually. So if you go and mark each of the peak, and now you have 4 peaks here, right? It may not be a exact double doublet, but it looks like a double doublet. You can calculate the coupling constant by taking the difference of these two and then multiplying with 600 megahertz. You'll get the coupling constant for this doublet. If you want to know the coupling constant of the bigger doublet, then 1 minus 3 or 2 minus 4 will give you the coupling constant of this peak, right? So let me try it and see if we can do it. So I click on the calculator, turn on the calculator, and you can see here, let me try it, 7.0169 minus 7.0128 is equal to this. Sorry, let me do it again. 7.0169 minus 7.0128 is equal to this, multiplied by 600 is equal to 2.46. So it's an aromatic region. This might be the meta coupling. This bigger doublet, 1.1 minus 3, should be equal to around 8 hertz. Let me see this. 7.0169. Now we have to take a difference with the third peak, this one, minus 7.0034 is equal to this, multiplied by 600 is equal to 8.1. And that is the ortho coupling. So ortho coupling usually is around 8 hertz, and the meta coupling is around 2 hertz, and that you just saw. So this is how you can manually calculate the coupling constants and the J values. And here, if you do the automatic coupling, it will show you the multiplicity of all the peaks. But if you go and select manual and then select a region, like for this peak, it will tell you the chemical shift value, that is 7.01. That is the center of this peak right here. And you can see here a small DD is written. That means that it's a double doublet, and that is what we calculated the coupling constant for, right? So we thought it's a double doublet, and we calculated two coupling constant values. Let me try this to another peak as well. So go to manual, and this should be a triplet, and yes it is. So you see this small t at 7.05. This should be a doublet. Let me select this one, and this should be a singlet. Yes, it's a singlet. And this one is a doublet. It's a clear doublet, right? This one also is a doublet. So this is how you can see the multiplicity of each of these peaks. So if you know that this is a doublet, you can calculate the coupling constant from here, and you can see that it's 7.7 hertz. If you double click on this, it shows you the coupling constant value, right? This is a double doublet, and if you click on this, if you click on this, you see the coupling constant values 8.1 and 2.5, and that is exactly what we calculated. 8.1, and I think it was 2.46. Let me see again. Yes, it was 2.46. So that is 2.5 and 8.1. So this is what we calculated manually. You can get it automatically from here as well, right? So these are some of the options about the J values. And then we have another option here, and from here you can select or edit the fit regions and so on. You can actually even draw the molecules in MestReNova. So you have these different options here about the bonds, the rings, the different types of rings you can draw. So if you have the structure and you want to keep it here on the side just to just for your convenience, so you can draw it from here. Okay, so these are almost all the options that we have. Now we have the proton NMR spectrum here. We need another spectrum like the carbon 13. So go to open, and it will take you here. Go to the folder. Here we have the carbon 13. Click on this, and you have these files. So you have to select the FID file. Click on this, and boom. So here we have the carbon 13 NMR spectrum of this molecule. Again, the peaks are pretty small, and you can see the carbon spectrum here, the carbon scale here. Here's the intensity. If you want to increase the intensity, again you can do it from here. So you can increase the intensity and so on, right? So this 0 is a little displaced. This TMS signal is displaced from 0, so you can bring it to 0. If you go and select this peak, which is for the solvent, and then go to reference here and click on this and select the central peak. Here you see the shift is 51.543. Go to solvents. You know that you have carried out your analysis in methanol, and now this list will give you the carbon values of these different solvents. So methanol appears at 49.00. Click select it and click OK, and you can see that it shifts slightly. And now you can see that your 0 should be exactly on 0, or your TMS should be exactly on 0, and here it is. So you see that it's exactly on 0. So now your spectrum is set. You bring it down to appropriate levels, and you can zoom it in, yeah, like this. And now you can do the peak picking just to know how many carbons are there and what is the chemical shift value. So you select this here. You can manually select all the peaks, or you can just click on this button and it will select everything, right, like this. Okay, so if again you want to increase the font size, so go down to properties and go to peaks, go to font, increase it to 14, and here it is. Okay, so here are all the carbon peaks. But again, if you do it manually, that's, I think, much better. This is the broadband carbon-13 NMR spectrum of this molecule. Now you have to differentiate between the different types of carbons as we have discussed earlier. And for that we have the depth 90 and the depth 135 spectra. Here I have only the depth 135, so I click on that folder, double click on FID, and here I have the depth 135 for this. I can also do the peak picking with this, so you can pick all the peaks like this. Yeah, and see the negative phase signals are not picked, only these are picked. So that is why I suggest that you do it manually from here. And now you see that 1, 2, 3, 4 signals are in the negative phase. That shows that this molecule has 4 CH2 groups. The rest are CH3s and CHs. You subtract all of these signals from this broadband carbon-13 NMR spectrum and you'll get the quaternary signals. Like for example, 167 should be absent in the depth 135, and you see there is no 167, nothing above 140, and that means that this 167 is a quaternary carbon. So we're done with the proton and the carbon-13, and if you want to analyze it further, you can also drag down some of the two-dimensional NMR spectra and you select the acquisition from here, double click it, and here it is. So this is the HSQC two-dimensional NMR spectra, and I would not go into the details of this spectra because we have not discussed it. We will discuss it later on in another course. So you can just play with the spectra like this, and if you want to correct the phase, you can do it with manual correction, and you see that these contours will shrink and it looks better now. HSQC is a two-dimensional NMR spectrum between, it's a heteronuclear two-dimensional technique, so it's between carbon and proton. So down here you will see the proton scale and here you see the carbon scale, and now because it's a two-dimensional spectrum, F1 and F2 will both be active. And also here this spectrum after second Fourier transform, it's also active now because now we have a two-dimensional spectrum. If you want to see your proton and NMR spectra here, so you can go to show traces here and it will show you the proton and the carbon-13 up here just for correlation with the peaks. But if you don't like it, you can right click, go to setup, and here you select proton, right, that is on the vertical trace, and then you select carbon-13 here, okay, and here go to setup and carbon-13. Okay, so we have the proton NMR spectrum here, we have the carbon spectrum here, and this is the correlation between proton and carbon. So you have this cross here as well. If you keep it on one of these dots, it will connect on one side with the proton like this down here at 6.5, and it will connect to this here, right? But if you think that the peaks are out of phase, so what you do is that you bring it here and you go to the reference, select this peak which you think is the peak for the solvent, and go to methanol 3. Okay, and it's set now, right? So no, it's not set. Let me do it again. This should be 4.8 here. Okay, now this looks good, right? So we have all the peaks around 7.5 up to 7.5 here, which was the case in proton NMR as well. You have the crosshair here, and you can now compare these proton and carbon values with this technique, right? If you want to insert another technique, go to open again and go to the cozy spectrum, go to acquisition, double click, and here we have the cozy spectrum as well. If you want to see the HMBC spectra, go back, and here we have the HMBC. Click on the acquisition, and here we have, right? So this is how you can drag down. You can also drag and drop spectra. So for example, I have this folder, open it. If you want to have another HSQC, click on this acquisition and then drag it and drop it here. So you see we have it again, but you already have it, so you don't want to have the second one. Control C will delete it, right? So this is how you can play with your spectra. You can extract maximum information about the structure of the molecule. We have not discussed the details of how to play with this COSY or HMBC or HSQC spectra. I'll tell you these details later on when we will be talking about these techniques in another course. So I think this is enough for today for a beginner. So thank you so much. See you later.